Oops, I'm recording it now. Well, thanks for joining the session and welcome to your first laboratory. As you probably know, we're gonna have labs every other week. So week 2, then next laboratory will be in week 4, week 6, 8, and 10. I'm gonna run the first 3 labs, and then another lecturer will take it over from me. Dominic Ong, so he is based at Nathan. So another thing that I would like to mention before we start going through the presentation. So tomorrow I'm going to give you a link to this first quiz, laboratory quiz. So there will be about 10 questions, and you're gonna have 1 hour to complete it. So you can, I think, start from 6 in the morning. I probably can do it even earlier, but I'm not sure if you'll be awake then. So just complete that quiz. Many questions are related to test procedure. So this is something that you can learn about from those videos. If you haven't watched those videos that I uploaded on YouTube, please do that. And also maybe do it like before you take a quiz, because it will save some time for you. Good morning. Yeah, good morning, everybody. So it will save some time for you. So just watch those watch those videos, YouTube videos, before you take the quiz. I don't think it's very difficult. Well, again, maybe for me not difficult, but we'll see how you will go with it. If for some reason you don't take the quiz, you, I don't know, sleep in until very late, or I don't know, you have something else, in this case, you'll be allowed to take this quiz next week, but you're gonna get maximum only 50% for the quiz, because it's just like considered as your second. Yeah, it's going to be available the whole day, so I'm gonna open it. I can open it like as early as 5 or 6 in the morning, and until the end of Friday, which is 23:59, so 11:59. But I'm not sure if somebody would like to wait until that late to take the quiz. And I'm going to give you answers. I'm going to upload your marks on Monday, because I still would like to go through all your answers and see like if like something is wrong or something is all right. So as I mentioned, there will be like many multiple choice questions related to the procedure of the test. Unfortunately, like this trimester, we cannot do it face-to-face. And well, I think it's like more fun when we do it face-to-face, because actually like students like do it by like themselves. They gain this like practical experience. But well, it's not like our fault. It's not your fault. I think we have to adjust to like these like circumstances that we have right now, this coronavirus thing. So well, we'll try to do it like with quizzes, and we'll see how it goes. This is going to be first time we'll do this online quizzes for laboratories, so hopefully it will be fine. But well, like we will learn from our mistakes, I guess. Okay, so what I'm going to do today is I will talk about site tests, something that we used to do like at Griffith in outside as part of our first laboratory. And then I'm going to talk about geological cross sections. So the first part, site investigation, site test, that will be in your quiz tomorrow, quiz 1. And geological cross section will be part of your project. So you probably know that you have also like a major item, which is project 1. So I think it's going to be due like week 7 or 8. And the first thing that you'll be required to do is to draw cross section, because I'm going to give you data from real site investigation, and you will need to analyze the data in your project. So, and if you don't know how to draw a cross section, that will be very bad because you're going to be assessed on this item. That's why a second part of today's laboratory session will be about cross sections. I will teach you how to draw a cross section, and I will talk about common mistakes that students make. Well, again, if you have any questions, guys, please type it in the chat, and I'll be happy to answer them. I did one session yesterday, so it will be sort of similar, but I would like to maybe have a little bit more of interaction with you. And I just want to start with this question: do you know how we study soils? I mean, how would you study, like, if you're asked to like study like some area because you plan to build something there? How would you like study what is underground? Get some samples. Yes, that's correct. Samples. How do we get samples? What would be like the best way to collect samples? Yeah, that's correct. We need to take samples. Core sampling. Yeah, that's very good. How many core samples would you like to collect? Yeah. Okay. Yeah, that's correct. So if you have a large area, a few hundred for okay. Look, if you have like area like this, right? And let's say this is 100 meters, and or maybe like okay, 100 meters, and this is also 100 meters. Where would you like to collect samples? Like center, okay. What about edges, like in the corners? So, for example, from here, you probably know what is in this around this area, but you don't know what is here, right? I'm talking about this is plan view. This is plan view. This is not cross section. So this is like if we look from the top, from the sky. So this is the area that we cover. Okay, so we know what is in the middle, but we don't really know what is in the corners. So ideally, if we can get samples from here too, that would be very good, right? Again, if we drill boreholes in these points, right, but we still don't know what is in between, of course, we can assume that what is in the middle and what is in the corners, this is kind of going to be like similar things, and we can just interpolate the results from in the middle. And here we just say that, well, maybe something is going to be like very similar. So this is how like we're going to cover this area. So the first thing that we would like to do is to take samples. So we drill a borehole, right? So if this is the ground, we're going to drill a borehole. And we collect samples from different depths, right? And then we're going to look at the samples, and we're going to see what's like sample we have, if it's what kind of soil it is, right? So if we have more money, we can drill another borehole and also see what is here, right? So this is borehole 2, this is borehole 1. Again, we know what is in this area and here this area, but imagine if this is like about 100 meters distance, we still don't know what's in between, right? Do you know any other methods that we can just, other than boreholes, that we can try to get a little bit of idea what is in between? Because maybe there is like same material that is in boreholes 1 and borehole 2, but maybe there is something different. And what if there is some kind of like soft layer of clay? And if we miss this layer of clay, there may be some issues when we build like high-rise building. So, any ideas? What else can we do other than boreholes? Boreholes is good, but remember that boreholes is probably like the most costly type of investigation. Yeah, boreholes are very costly. So for like small houses, you're probably gonna have maybe like 1 or 2 like boreholes that will drill it for you to do some site investigation for small houses. But for something bigger, larger, you probably need more boreholes. But there's other methods. I'm not sure if you heard of geophysics. Have you heard of geophysics? Like, waves that go through like different media, like seismic waves? Well, I'll take it as a no. Yes, okay. So there is another really good method of investigation. It's seismic waves, geophysics. We don't really need to excavate anything. So what we can do is I'm going to change the color. We put sensors on the surface. They're like about 1.5 meters away from each other. And then we're gonna have, we need to generate some wave. So what we can do, we can have a big hammer. Somebody with a big hammer, somebody very is going to hit the hammer against the ground, and it will generate waves. So, and then we're going to measure how these waves travel in the soil mass. So how fast they go to each of the sensors that we measure the waves. So in this case, by measuring the wave velocity, we can have some idea about the different types of soil. So just by seeing that, okay, so in this case, like one wave will be maybe 150 meters per second. So in this area, waves will be about 300 meters per second. And here will be 1,000 meters per second. So we can define these areas. And then if we look at boreholes, we can actually confirm these areas with the soil or rock that we know. Just kind of like a question for you guys. What kind of, if we have rock and we have soil, in what material do you think wave will travel faster? In harder rock or softer? Yeah, it will be a rock. Yeah, rocks. Yeah. So what we do is, unfortunately, this geophysics are not going to give us the type of soil or rock. We just like don't know it. We just need to drill borehole to look at soil or rock. But it will give us these velocities, and we already know this correlation because we've done these methods like thousands of times, and we can correlate each velocity to like certain type of soil or rock. So we can at least have some understanding of this. So we can say that, okay, if it hits like this number, so it's going to be very hard material like rock. If it's kind of like very like low, well, like sort of like low numbers, that will be soft material. Okay, so there are a few more methods that we'll talk about today, and I think the best one is like for you if you know the standard. So we just follow the standard when we do site or field site or laboratory investigation, geotechnical investigation. Well, it's mostly like site investigation. So it will teach you how many boreholes to drill. It will teach you how deep the borehole should be, depending on the type of structure you design, what kind of and how many samples you need to take, how to describe the samples based on their properties. So everything is in this standard. This standard is available at any geotechnical company, and they follow this standard. So even if you, let's say, like don't know how to do that, just read the standard. It gives you a good explanation of the work. Another thing which is important for site investigation, this is actually something that we need to do before any site investigation. We need to find geological maps. In Australia, we can find geological map for any area, for any territory. They're all covered with a geological map. So we just need to find like what area in particular we're interested in, and I think we can buy it. We can buy a map from I think it's called Geoscience Australia or Geological Society of Australia. They sell maps. Usually like $25–50 for each area. So this is actually also like the first thing that you really need to do, because it will already give you lots of information about type of soil and rocks. Typically it's covered in this legend. You see, if you look at geological map, it has a different color. Color typically stands for the age. So when that rock or soil formation was formed, it's like million years ago or 10 million years ago. Another important thing about geological map is cross section. So this one, this line. So geological map is good because, well, it kind of shows you what is on the surface. But in geotechnical engineering, we often work with underground surfaces. So, I mean, with the underground. So we would like to know what is below the surface. And this is cross-section for each geological map that would show you what is beneath the surface. And this is something that you will be required to do for your project number 1. So here you have depth. So this is depth. And this is distance. And it starts from point A to A dash. So point A is here. A dash is here. And then it shows you what is underneath the surface. This one goes for 1,000 meters, which is very good. So it kind of gives you some idea about how these formations, rock formations, they like place against each other. If you see, because this one actually goes like deep in at some angles. We wouldn't know that if we just look at the surface. Like at the map, we don't know that they are deepened at different angles. And when we see things like that, this is actually not very good because all these like folds and deepening of rock strata or soil formations, that's not very good because it makes soil or rock weathered and loose. So that's how like we know that, well, this area may be a little bit dangerous. So we need to do something about it. Okay, so this is geological map, and this is boreholes. It's the kind of samples you see, the samples that we take, we put them in the box. And this covers, it starts from 0, which is, this one, starts from the surface ground to 1 meter. Then next run is from 1 meter to 2 meters. Then from 2 to 3 meters. So, and then so on, 3 or 4 meters. So we can take this sample from the borehole and we can look at it. And we can describe it, and we're going to record it in this borehole log. So this is just example of borehole log. You'll be given this borehole log, borehole logs for your assignment, which is project 1. And you will need to know how to interpret this one and read it. So all the important information about borehole is given here. So here it's a depth. Let's say if you start drilling from here, goes all the way down. So this is the surface. If it's, we'll say it's a 0 meters, so it goes down like 1 meter down, 2 meters down, 3 meters down. And whatever we get, soil or rock, we can map it. So in terms of the depth, so this is from 40 centimeters. We have the silty clay from ground to 40 centimeters down. We have another silty clay here. We also look at the moisture. We have symbols for this one, moist, moist. We have W means wet. And we have also consistency, because when we take sample, collect sample, we also fill the sample. We do some visual examination, and we also feel it with our hands, where we can say if it's like stiff, ST, or it's firm, or VL means very loose. So we describe as much as possible and provide lots of information in this borehole. Each borehole comes with a legend. Let's say if you don't know what M means, you can look at the legend. So a legend is always attached. Also the symbols CH, CL, this also related to the properties of soil. And this is something that we'll talk about in week 3 when we classify soil. So all the information about soil or rocks is given in this borehole. So this is very important piece of information, and that's why I would like you to learn how to read it and how to interpret it. So later in the second part of the session, I will show you a few examples and I will teach you how to draw a cross-section based on these borehole logs. And then you will practice by yourself for your first for project one. Another thing that is shown here, this one is SPT test. SPT stands for Standard Penetration Test. And Standard Penetration Test, you'll talk about it more in the next course, Geotechnical Engineering. So you will see how we use this data from SPT test and apply it for design purposes. So I can only tell you at this point that this is the kind of test, like similar to what we'll talk about today. We'll talk about DCP, which is dynamic penetrometer test. This is something that everybody can do. It's like mobile test that you can bring to any site. SPT, it's mounted like on a truck, so it's like a big rig that you use to drill like boreholes and perform this test. And it also gives you this number of blows. In this case, n is equal to 2. This shows the strength of soil. So as you will see today when we do DCP test analysis, so when we have very low n, like n is 2 to 5, it means that soil is not very strong or soft. Then you will see that denser soil will have like much higher values of n's, like maybe 10, 15. And then when we go to rocks, then we just cannot penetrate it with this test. So it will be like 40 number of blows will be 50, and at that stage we just don't do the test anymore. Another thing that I would like you to pay attention to is pocket penetrometer test results that we will do today, and it will be in your quiz tomorrow. So this is a good test. Engineers do it. They collect samples from the borehole, and then they perform this sample on the they perform this test on the sample from the borehole. Okay, so this is sorry, another thing. Groundwater. Where is groundwater here? Okay, there is no groundwater level here. I will show you in other borehole logs, and in your borehole log that you'll be given for your project one, there will be another column somewhere here that will show you groundwater level. It shows where the water is in soil. So you may be aware that there is always water in the soil, and it creates groundwater level. So which means that soil below this groundwater level, it's saturated. So this is also important information. This is something that we need to know when we calculate stresses in soil, and I will teach you how to do that later. Okay, so I'm going to my slides for today's recovered column represents. Recovered column represents it's the sample that was collected. So they collected sample at this level and collected sample at this level. So it's a U50. So maybe like the way they drill it, they just drill until 1 meter. That's auger drill, and they didn't collect, like good quality samples. So there is like different ways to drill. Yeah, there is like different ways to drill boreholes. If you collect constantly collect samples, that's more expensive. The one that we can do, they just drill to 1 meter, then they will just do this SPT test, and at the same collect sample. Then they drill another until 2 meters here, and then they will use like a sampler to collect good quality sample. So whatever they drill till 2 meters, they just like dump it, like they don't really need it. They just like, because like the way like the soil is all mixed, you can't really tell what it is. But this is a good samples that they just recovered. Okay, some dynamic on penetrometer tests. The first one we'll do, and there's a video of test procedure, pocket penetrometer, vein shear, and water moisture content. So all this will be in your quiz. Either it's multiple choice question about test procedure, or for water content test, I'm going to give you some data and you'll be asked to give me water content. I will show you how to do it today. Okay, so we'll start with dynamic on penetrometer. So this is the device. So it has this rod and it attached to the knocking head. And on top of knocking head, there is a hammer. So hammer, we lift the hammer manually and then release it. It goes down, it falls down, it hits the head, and it will generate some energy force that will drive cone down. So what we do is, in the video, you will see there are marks here, and each mark is 10 centimeters. So 10 centimeters, 20, 30, 40. So what we do, we just count the number of blows of the hammer to drive the cone in the ground by 10 centimeters. So when it goes all the way down until this level, we just need to know the number, let's say number 2. So it means that we just need like 2 blows of hammer to drive it in the ground by 10 centimeters. Then we just start counting again. So we'll see how many blows we need to drive the cone down by another 10 centimeters. And we just continue this test. For soft material, you will see that test will just go very quickly. It will be maybe 1, 2, 3 blows, and it will just go down because it's soft. For denser material, we will need higher number of blows. And at some point, we're going to hit maybe like very hard material or like even rock, at which point we cannot really go down anymore. So at this point, we'll have to stop the test and just pull it out, the rod, and go to another place. In this case, we can go and do test here, another maybe 1, 2 meters, or another good thing, we can bring it here and do test here. So this test can cover large area, and it's pretty simple and it's fast. The only problem with this test is you need to know when to stop. So I already told the story yesterday at like first laboratory. So this is what happened. That's we are doing this test, DCP test, many years ago. When I just joined Griffith and I didn't have much experience with the soil here on Gold Coast. So I thought we could go like very deep. We can go to like maybe 4 meters because the soft soil wasn't like very hard to penetrate. And we did the test maybe for like 10. I think we went down by about 4 meters. And then we were like, okay, so we hit some hard material. Let's stop the test and pull out the rods. And then we like spent about 1.5 hours trying to pull it out, but we couldn't because we did this test in this soft clay and it was like saturated. I mean, it was moist. So it applied very high like force to the rod. So we just couldn't pull it out, so we just give up and we just left it there. So it's probably still there. That's low. And the worst thing is that I just bought that this device like 3 days before we did this test, and it was gone. So I was very disappointed, but I learned my lesson. So usually now we don't go like deeper than 2 meters. So 2 meters would be like a kind of even though it's still soft material, we will just stop at like about 2 meters. 1.5, 2 meters would be good for the soil that we have on Gold Coast. I just didn't know that because we did many tests in Japan on sand, And for sand, we could go like deep, like 2, 3, even 4 like meters. And then that was fine to take it out from the ground, the road. But for this one, it's just also you need to be careful with the type of soil you deal with. So I think 2 meters should be just right. So this is the kind of results that we can get. That's what we get from that very expensive test that we conducted. That was like almost like $1,000 worth. This is the data. So for each 10 centimeters that we penetrate the ground, we just count number of blows, and we plot it against the depth. So actually in that test, we went to almost till 5 meters. That was really crazy. So don't do it. Don't make like the same mistake as I did. So the good thing about this test is it can give us some estimates of the soil strength. So if we know that the number of blows about like maybe 2 or 3, so we already have some correlations. We have some relationship, empirical relationship. If we know the type of soil, for example, clay, we can have some idea about its strength, just looking at the numbers of blows. Another good thing about this test is that you see how this one goes almost to 3 meters. It goes, there is some variation in the number of blows, but it only from maybe like goes from maybe 2 to 4, right? So it's kind of looks like it's like same material or something very, very similar. And then you see at here at some like level from 3 to 4, you will see some changes here. So in this case, you have already a little bit a different level of different number of blows. I think it's about 10. At this point, you have like about 10, right? And then you will see that there's going to be another change here. So that will be about maybe 22 blows. And at some point, goes to almost 40. So what is good about these numbers is that we can pick up the boundaries. So we know that there is going to be a boundary between different soil or rock formations, right? The bad thing about, well, not the bad, the disadvantage about this test is that, well, we don't actually know what soil or rock it is. So if it can be clay or can be sand, can be like mixture, can be silt, we don't know because we don't take any sample. We can just know the boundary. We know that at level of 3 meters, there is a boundary between 2 different materials. But what material they are, we don't know. So that's why this DCP test needs to be conducted together with maybe boreholes. So let's say we drill 1 or 2 boreholes, and then we will cover the rest of the area with this DCP test, because DCP test will first give you some idea about the strength of the soil, and it will also confirm the boundaries between different soil formations that we can find out from the borehole. So from the borehole, it's easy. We look at, well, this is sand or this is clay, and the boundary at 3 meters at this borehole. And then we do this DCP test, maybe 1 or 2 meters away from the borehole. And then we notice there is a boundary between 2 different materials at the depth of about 1 meter. And we'll be like, okay, so it probably like same sand on the top, and below it's like a different material. So DCP goes really well with boreholes, but by itself, it can only give you like the boundaries between different soils or rocks, but it's not going to give you any idea about the type of soil, if it's clay, silt, gravel, or any type of like weathered rock, unfortunately. You have any questions? No questions? Okay, if no questions, then I'll just go to my next slide. So what we did before when we had face-to-face labs, students actually will do this test. We have these pits just in front of our laboratory outside that we built a few years ago, so that students can do this penetration test. I'm just going to show you what kind of data they used to get and how to analyze it, because you'll be probably asked to do it for your first project one. And at least there will be a question about test procedure in the quiz tomorrow. So let's say that we start from the surface, and number of blows to drive the cone by 10 centimeters down will be 1. Then we'll do a little bit denser, we need 2. Then for next 10 centimeters, well, again, maybe 1. Then 2, then 3, 2, 70, we have, let's say, 5, 6, 5, 8. Here we have 12, 15, 16, 15. So, and then we just go like down, 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 down. So we're first going to plot the data. And the way that we plot data is we're going to put here number of blows. And at this point, we're going to write depth. I'm trying to write depth here. Will be in centimeters. So what we can do is just define the scale. So we have maybe 10 blows. That will be 10. It's not very good drawing. I think I should have put, and here will be 20. And here will be 10 centimeters. 0, this is going to be 10, 20, 30, 40, 50, and you go down, right? So if you do it at home, you can use, for example, Excel. That's okay. Or you can draw by hand. Doesn't matter as long as it's correct. I will be very happy and satisfied. Just how you draw it, it's up to you, but it should be like nice and clean, like not like the way that I draw it right now on the screen. This is really bad. If you draw something like that, you're just gonna lose many points because it doesn't look good. It also should look very nice. So we start with number of blows, and 1 I think will be like here. So this is 1 number of blows. That's until 10. Then till 20 is going to be 2. Then it goes again to 1. Then again to 2. Yeah, it's kind of like that, but we draw this like straight lines. So maybe you don't see straight lines. Yeah. From 40 to 50, it's going to be 3. Then again 2. Then you will see that there is going to be increase to 5. Again, should be straight line. 5, 6, 5. Then it goes to 8. 8. Then it goes to 12. Somewhere here. Goes to 15. 16, 15. Okay. So, and then maybe it will go even deeper. So all these lines should be straight lines. So mine are not straight because, well, maybe I don't know how to. It's very difficult for me to draw a straight line with my pen on the Surface, Surface Pro. So, but it should look very nice. So like the one that I showed you before, like my data, like of the test that we did in the Tambourine Mountain, it should look like that. So after that, what you do, it's not like you just like plot the graph and like you don't analyze it. You still need to do some analysis, and you need to have at least some idea where the boundaries are, right? So you will see that this part kind of goes 1, 1, 1, 2, and then it changes. Then it goes sort of like this, changes. There is some kind of increase here, not sure what it is, and then it's like this, right? So we can sort of pick up these boundaries here. I don't know exactly what it is because we just have this data and we don't know the type of soil. For example, like now I can just say S1, S2, S3, but it's not something that you need to do like when you work on a real project. On a real project, you're going to look at the borehole data. Usually there should be borehole data. If there is no borehole data, you cannot like say anything then. You can just only like pick up these boundaries, like lines. That's it. But without knowing what soil or rock it is, it it kind of gives you some like idea like how like soil formation is underground, but you just also need to know like if it's sand, clay, or like things like that, right? So this is something that you would need to do like if you are given this data for your project one. Also, if you, let's say, work in the industry, like geotechnical engineering or like something similar when you deal with soil, at least you know how to analyze the data from this DCP test. It's very commonly used, like Gold Coast, Brisbane, many like small companies, they use this DCP test. They just go to the site, do as many tests as they would like to. They would get some idea about the strength, and they're gonna use this value. There was a question. Let me just read the question, guys. This may be not exactly in the first section of the graph. Why isn't it a straight line down from depth 20 to 40? I think this one was 2. I think the way I wrote it was 2. That's why I didn't do it the same. This is 1. If it's 2 and 2, then it's going to be straight line. That's correct. I thought it was 1 and 2 when I look at my handwriting, and I was like, looks like 2 to me, but maybe 1. So if it's like same values, then it's going to be just like straight line, correct. But in the visual graph it is. In the visual graph, the one from 30, okay, so how about then we'll change. So this is 1, 2, 1, 2, then from 40 to 50 is 3, 2. Well, yeah, I mean, when you kind of like show examples, it's a little bit it's a little bit difficult to draw it like accurately. Like I draw it on computer, and it's not very easy for me. But when you just like write it on a piece of paper, that should be all correct. Excel will be good if you can draw such graphs like the one that I showed you before. I use Excel to draw that one. We just it looks very nice, and you can make it look really nice. If you don't know how to do it in Excel, just take a piece of paper and like draw a graph like by hand. That's also okay. Okay, so going then to next slides. Okay, pocket penetrometer. Actually, many geotechnical engineers and geological engineers or like practitioners, they like using pocket penetrometer test. Why? Because it's a very like small and portable device. You can put it in your pocket, pocket penetrometer, and then you can bring it to the site. And it's going to give you, again, some idea about the strength of soil. So whatever test we're talking about, it's mostly about how to measure the strength of soil. So because this is probably like one of the most important things in engineering, the strength. So the test, it's again, just guys watch the video. There's I talk about pocket penetrometer. This is just another type of pocket penetrometer. This is the tip that we press against the soil. and then we'll see the resistance of soil measured by the scale. And this test needs to be done at least like 3 times, and we'll take the average value. So don't just like rely on one test. So in actually like geotechnical engineering, because we deal with nature and soil properties, even like within maybe 10, 20 centimeters of soil mass, they will vary. That's not going to be exactly the same as, let's say, for concrete or for steel. We know that the properties are the same, but for soil or even rocks, but mostly for soil, you will see there is like properties change a lot. So that's why it's very challenging for geotechnical engineers to do all the design, because like imagine you deal with like large area like 100 by 100 meters, and you need to like design a structure that will be in that area, and you need to have a reliable geological model of that area. But what we can see is only what is on the surface, and we can get a little bit of information about what is underground, but we're not going to cover the whole area. So we can miss something. There have been cases when maybe like you hear about collapses of structures or like sinkholes. It's because during site investigation they missed maybe like a very thin layer of clay. They just couldn't pick it up with boreholes, because those boreholes, when they placed boreholes around that area, they just couldn't like find that clay. It was like located like in that area, but not in the like spot where the boreholes were drilled. So there have been many cases like that, and they talk about it all like those like sinkholes, when they just like don't know about those like things that is like going on underground, because they just cannot cover the whole area. I mean, this is really difficult, and that's why it's very challenging, because we have to do lots of assumptions, and we need to do some we need to like simplify things and assume that maybe like what we have in this borehole will be the same thing in the whole area, but well, maybe that's not right. So what I was talking about? I was talking about, I just lost already my idea. So my point is that the more tests you do, the more reliable values you get. And for this pocket penetrometer test, it's recommended to do 3 tests on the same soil, just maybe a slightly different location. You do this test, and the good thing about this test, we can correlate these PP values to unconfined compressive strength. So pocket penetrometer values by itself will sort of give you some idea about the strength. Let's say if it's like this soil will have only 10 kPa, the other soil is going to have 200 kPa. Like definitely there is like a big difference. But unconfined compressive strength, it's more commonly used for design purposes. So if we get some value of pocket penetrometer, we can change it to unconfined compressive strength. Guys, do you know like what like kPa for what do we measure with in using kPa? Anybody knows what kPa we use for? Pressure. Well, I don't think, I think the correct word will be stress. Stress, we use kPa, which is also kilonewtons per square meters. That's correct. Yeah, so yeah, that's correct. So for soil mechanics, geotechnical engineering, rock mechanics, we need to use the stresses. We use stresses because we need to know like the stress that is acting on soil or rock, and that will also give us the idea about the strength of soil and rock. So if it can bear the stress, so that's very good. If not, well, it will collapse. So for PP values, when we do the test in the field, the one that was in the video, we get kilogram force per square centimeters. Let's say in the test that I did it was 1 kilogram force per square centimeters, the value. How do we convert it to kPa? If we convert it to kPa, what will be the value? Anybody knows? 1 kilogram force. How many kPa? Google. Yeah, guys, this is actually like very good idea. That's what I do sometimes. I just Google it. You just like say convert kilogram force per square centimeters. So another thing is I put it in the notes for the laboratory. I'm not sure if you read it. It's if you go to the first laboratory, there is kind of like a data sheet. So it should be 98 kPa. So if we get values in kilogram force per square centimeters, what you just do, just multiply by 98 and change it to kPa. That's correct. kPa 98. So we can just round to 98. Okay, so another thing that you should be aware of, how to convert it to unconfined compressive strength. So you get these values of pocket penetrometer. Let's say we change it to 98 kPa, which is 1 kilogram force. We measure in the field. Then we change to kilogram 98 kPa. And then next thing is that we just convert to unconfined compressive strength. And we're going to use these empirical correlations. These two commonly used. The third one is for clay, which is with lots of cracks. Usually we don't deal with, well, it's not very common. But like this one that says in general, it's more kind of like a natural soil that like we deal with. Fill, it's the material that we bring from somewhere else. That can be that natural soil that we fill it, bring it from somewhere else, and then we place it to fill some area. And usually we would compact it, make it a little bit stronger. So this is something that was brought from somewhere else, fills. So like we say, like we fill for like maybe like a dam or like for retaining wall, we bring that material from somewhere and put some fillings. Or if we want to build something and the surface is uneven, we're gonna put some fill in there to make the surface even, and then we build on top of that. So if we, for like all natural soils, what we do is we take 98 kPa and multiply by 0.8. I don't know how much it's going to be, but that's going to be the this unconfined compressive strength, QA. If we have, if we do this test on the fill material, then in this case we take 98, the value that we measured, and multiply by 1.15, and we get this unconfined compressive strength for fills. I forgot to ask you guys, do you know what is unconfined compression test? When I asked yesterday, people said, well, we don't know. Anybody know what is unconfined compression test? No. Okay. So this is the kind of test that you will do. Well, if you take rock mechanics course, I do this. We do this test on rocks. I think we also do this test on concrete. So unconfined compression is that we take a sample. It's a sample, and then we just put it on in the machine pedestal, and then we apply load stress in the vertical direction. We call it vertical stress or sigma 1. Sigma stands for stress. And we apply it only in the vertical direction. So when we sort of apply stress, it will soil or rock will develop this failure envelope and like collapse. So you see cracks here, and then it will collapse. So we can do it for soil, we can do it for rocks. So it's very common for rocks or for concrete. So we can develop this, we can make this cylindrical samples, and we do this unconfined compression test. It's very quick. It's commonly used in the industry because it's well easy to do, and it also correlates to all different parameters of soil and rock. If we have another test, and if we apply confining pressure from both sides, which we call sigma 3, or confining pressure, in this case, it's not going to be unconfined compression anymore because we can confine the sample from the site. So this is actually what happens in real life in the field, because I'll talk about it later. But if we take sample, this is the ground, right? If we take sample from here, we always have vertical stress acting on the sample on the ground, and we have lateral stress. So ideally, we would like to do tests where we have also confining pressure. We can do that as well. We have a machine to do that, but it's time consuming. It will take about 2 or 3 days to do this test. While unconfined compression test is very quick, and you can get also good estimates of strength. Do you think, why do you think we can do this unconfined compressive strength only for clay? Why do we never talk about unconfined compressive strength of sand? What do you think? Why this test like the one that like without confining pressure? With confining pressure, we can do it for sand. Just it's unconfined when we just only apply stress in the vertical direction. Any idea? I wouldn't say dispersed, but that's correct. Because sand is a granular material. It will just it cannot hold this shape, right? Yeah, it will just like kind of like fall, like slide down. So it won't sand. It's not capable of holding shape like the one that we require for this test. Only clay can do that. Clay, especially clay when it's a little bit wet. So because clay particles, they are cohesive, so they have cohesion, so they can actually hold each other. So they can hold the shape, like any shape. But for sand, there is no way it can hold any shape. It will just like slide down because of the gravity. There is no like any force acting between sand particles that will hold it together. But for clay, yes, there is some electrical forces action between clay particles that will hold it together for this shape. Yeah, that's correct. That's why we do it only for clay. And for concrete and rock, because it's hard material, so we can you just hold this shape. It's not because of the size. Well, of course, like sand has like larger size than clay. Like clay is like smaller by like I don't know, like 1,000 or like 10,000 times than sand particles. But it's also, well, because it's a very small particle, clay. You can't really even see it with like naked eyes. So it has this special structure, and that special structure, it generates a negative charge. So, and this is because of these chemical forces acting between these particles. They can also hold water. So if you think about sand, sand cannot hold water. Water will just seep through the sand, that's it. But if you add water to clay, water will stay in clay. It's because those negative charges will act with molecules of water and hold it together, and also hold those particles together as well. So that's why clay, it's always problematic because it can hold water, and when soil has water, it's not very good for its properties, because water will decrease the strength, will make soil like more plastic and things like that. But sand, just water, just like drains through sand, and that's it. And it's good to like to go. Okay, I'll go to next slides. Okay, so yeah, just like remember this this table. It may be useful for your quiz tomorrow. Just give you some tips, guys. Look at this. Vinci test. Well, this is actually myself. I'm not sure if you met me in person. Probably no, you haven't yet. That's me. And I'm not going to talk about Vinci test. There's not really much to discuss. It's kind of pretty simple test. I would like you to watch the video. Please watch it because there will be questions in the quiz about Vinci test. It's only like less than 2 minutes. And there is not really much to talk about. It tests again that will give you some idea about the strength of soil, something that we can get with a pocket penetrometer, and we already talked about pocket penetrometer. So then going next, and the other one already 10. The other one test that which is actually very important when we collect samples from the field. We would like to know the water content. I mean, we would like to know like other things like degree of saturation, density. But for this first laboratory, we just do a simple test to measure the water content, right? So the way we'll do it, we'll just collect sample and then we're gonna put it in oven and dry it up. So before we need to know the mass of soil, then we put it in the oven. We set temperature 105 degrees Celsius, and we wait for 24 hours. 24 hours. So we just follow the standard. Then we'll take it out and we measure the mass again, and this is going to be mass of dry soil. And then what is going to be the mass of water? Yes, so it's going to be mass of soil minus mass of dry soil. So this is mass of water. And what is about mass? So this is what we need to get. What about mass of solids? How do you get mass of solids? From where we get mass of solids? Sample, that's correct, yeah, from sample, but what's it called? Not initial, because initial it's mass of soil, initial mass of soil, and mass of soil includes mass of water and mass of solids. We just only need mass of solids. So we took the difference between total mass and dry mass, and it gave us the mass of water. But now we need to divide it by mass of solids. So how do you get mass of solids? The mass of yeah, that's correct. So mass of solids, it's mass of dry soil. So because when soil is dry, there is no water. There is still some air in that soil, but air has no mass. So in this case, mass of solids is equal to mass of dry soil. Okay, so it's good that you understand this one. So it will be easy for you to do this analysis test. So what we do, like face-to-face laboratory, students measure mass of container. So they do 3 tests. Again, you need to do at least 3 tests. Like 3 tests should be enough. Don't do 1 or 2 because you want to get reliable data, and there is always variation. Or what if you didn't do it correctly? So it's not gonna be like enough to do only 1 test. So you do at least 3 tests according to the standard. If you do more tests, that's even better, but 3 should be enough. So in this case, we do 3 tests, test 1, test 2, test 3. And then we measured first the mass of empty container. So for the first test, it's same soil, but we just do like 3 measurements. So we have mass of containers. There's we have mass of wet soil plus container, and have mass of dry soil plus container. So how about I'll give you like a minute or 2, and you'll give me at least 1 value of water content. Can you guys do that? This is something that you'll be asked to do in the quiz as well. So let's practice. $46.9. No, I think it's a little bit like too high. So Anybody else wants to? It should be like 20 something to give you like a hint. 20. Well, you just calculate. I will start drawing the formula. So this is water content, mass of water divided by mass of solids. So mass of water is no 15, no, should be 20 something. So mass of water will be mass of wet soil minus mass of dry soil, right? They both have containers, so we just include it. So this is mass of water. Yeah, 24.4, very good. Mass of soil. No, because it's just mass of container. We just need mass of container because we put soil in the container. We need to put soil in the oven, so we still need to put it inside the container because how else we can put it in the oven? So that's why we just first measure the mass of container as well, because then we just do the calculations. It will be easy if we know the mass of container because we just deducted from the like for the mass of water. We don't really need to know the mass of container. We just look at the difference between mass of wet soil and mass of dry soil because they both have container. It's same thing. And yeah, for dry soil, yeah, you need to subtract, deduct. So it's going to be mass of dry soil, and you need to remove mass of container because this one has dry soil and container. This has container, so we just need to have dry soil. Yeah, 24.4. That's correct. 25.3. For water content, when you use percentage, just use only one decimal number. That's a standard way to present it. The test is not that accurate, 24.2. And then we take average out of the three, and average will be 24.6. Okay. So guys, well, I hope you understand how this this is how it works, right? So just be careful with the containers. This is a typical procedure. I think when we did some exercise yesterday in the lecture and or tutorials, we really don't talk about mass of container. We just say, well, mass of wet soil, mass of dry soil, but we just like sort of like simplify like the whole thing. But the way like when we do like real tests, we put soil in a container, so we just need to also include it in the calculations as well. And you will see it for other tests as well, for plasticity test, for compaction test. It's just because we need to measure, we need to put soil in the oven, and we can't just like leave it as it is. We just need to keep it in the container. But for like those like textbook examples that we do in the class, in the lectures, yeah, we usually don't talk about containers. We just ignore it because we just don't want to like waste time on just doing these calculations. But this is the real thing from the test, and if you know like how it goes, that will be really good. Okay, that's it for my slides for the test, and I have another set of slides, the one that I want to talk about, laboratory cross section. Do you have any idea how to draw a cross section? Maybe you have done it for some other courses, like cross section through some area. No? Okay. So cross section, it's something that would look like this. So you have ground here, and then you have a borehole, boreholes. Then maybe borehole 1, borehole 2, borehole 3, and then you have like something like this. So maybe this is sand, sand, sand. This is maybe clay, clay. So this is something like borehole, and of course it comes with a scale. So this is elevation. And don't forget to put units, and this is going to be distance in minutes. Yeah, so this is going to be cross section, something that engineers do like in real life, and this is something that you'll be asked to do for your project 1, and for project 2 maybe you're not asked to draw cross section, but whatever we're going to do in this course, it's all related to the underground surface. Sorry, not to the underground, so like all this area. So this is what we deal with. When we do the course, we will, for example, would like to know what is stresses at this level. And if we have a clay here, if we apply some stress, what is going to happen to the soil at this level? If there is going to be any landslides. So everything that we deal with is with underground. That's why this is the first step, and it's a very important step to draw a cross section. If you cannot draw a cross section, you won't be able to analyze any data, and you won't be able to come up with any design. So that's why I'm going to spend some time today explaining how to draw a cross section, and you will practice it for your first project. And at least, even if you are not geotechnical engineers in the end, so at least you know how to read cross section, because cross section will just give you a very good idea about geological model. And if you deal with water or structures, you still need to know like what is underground. Let me just share with you. I'm going to share my screen with you. Let me just see how to do. Share screen. Okay. So if you're going, if you go to the course content, and you will see this laboratory 1. Well, you also see lab notes. Maybe you didn't see that one. Sorry, not on this one. Sorry, that's a mistake. Test data sheet, laboratory fieldwork. So this is something that we did with students outside face-to-face. And this is the test they performed. They also performed water content test. And there is a table here for pocket penetrometer. And this is also, I put this conversion factor, kilogram force from square centimeters to 98 kPa. So it just for your reference. You may not really need it, but you never know. And another one is map and borehole logs. So another thing that we did in the laboratory, I would ask students to practice a little bit in the laboratory to draw a cross section. So this is taken from one of the projects a few years ago, and you're gonna have like a similar like set of data. So it's not exactly this map, and this map comes with boreholes as well. You see, this is boreholes, but you'll be given the map and you'll be given boreholes as well, but they will be different. But the procedure is the same. So once you know how to do this procedure, you should be able to do well in your project. So you see there is a map here, and it has these lines, and lines has numbers 1.2, 1.4. So this line shows elevation. So it's 1.4 meters above the sea level. You also see that BH9, BH1. So this is the location of boreholes. So that's where boreholes were drilled. You see this blue line, A dash. That's a cross section, and you need to draw. Sorry, that's like a line along which you need to draw a cross section. So you need to start from here, where it says A, and go all the way to A dash. So the way you draw a cross section, you see where this line crosses all the elevation contours, and you pick them up first. So there is many here, and then goes here. Then you see like where it crosses borehole. Another one crosses this borehole and also the elevation line, and goes all the way to the end of. So you need all these points where the line crosses points, elevation lines and boreholes. You need to pick up those points, and then I will show you later how we analyze it. Another thing, it's a scale. Each map comes with a scale. In this case, it says 1/4000. And again, I'll teach you a bit later what it means. These are boreholes. So this is borehole 1. You see BH1. So BH1 is located here. You see this BH1 doesn't have any elevation next to it, but like, for example, here BH8, it's not on the elevation line. So it says BH8, where it was drilled, the surface has elevation 1.76 meters. So all boreholes, they have information about elevation. You see this says borehole BH1, elevation 1.4 meters. So you also need to use. Each borehole comes with a legend, because there are some symbols that you may know. So all the symbols need to be explained, and I'll explain this for you. You see it has here PP, which means pocket penetrometer values, and you already know what pocket penetrometer means. Well, that's about it. So you are given this information. This is from real site investigation. Well, I just of course, did a little bit of I modified it a little bit, but this is from one of the areas on Gold Coast. And just to show what, and then I want to go now back and share my presentation with you. So I'm now going to explain how we draw cross-section. We'll go to next. So what I'm going to do now is I'm just going to use only half of the map. Usually it goes, let me change, should probably go like this. But I'm just going to deal with a left-hand side part. It can also go to here. So we're not going to look at the just I cut in the center, and we just only look at this part. And you do the same thing for the right-hand side. So first you look at the scale, and scale says 1/1500. So what it means is that the way I read this scale, I remove two zeros from the right, and then it's going to be 1 centimeter equal to 15 meters. So on this map, if we measure 1 centimeter, and let's say we just use a ruler, if this one is 1 centimeter on the map, so for the cross section, it's going to be 15 meters. So this is what it means. If it says you have a scale, the one that I showed you from previous years, it was 1/4000. This means that 1 centimeter is equal 40 meters. Again, removed zeros. So you need to know scale when you draw cross section. So next step is you start, as I said before, you need to see where this cross-section line A and A dash crosses elevations and boreholes. So this is point. I can call it point 1. Then another one, point 2. Then this one is point 3, point 4, point 5. Then if it goes here, then 0.6, 7. So you need to like pick up those points, and you just like the way I do. I just put the ruler. I print out the map. I do it on a paper. I put like a ruler. I'm drawing the ruler, right? And then set this for 0, and just measure the distances between all these points. I do it at once. This is much faster and more efficient. Say this is this distance 1 centimeter. This is like maybe will be like 1.8 centimeters. This will be 2 centimeters, 3 centimeters. And then you just like write it down. For example, from 0 to 0.1, it's 1 centimeter. From 0 to 0.2, let's say it's 1.8 centimeters. From 0 to 0.3, it's 2.5 centimeters. It's just example, right? From 0 to 0.4, let's say 5 centimeters. And then you just continue this way, right? Until the end. And then what you do next is you just multiply it by the scale. So if your scale is 1 centimeter is equal to 15 meters, you multiply everything by 15, by 15, 15 by 15. And you're going to get distance in meters. So 1 times 15 will be 15 meters. Then 1.8 times 15, I don't know how much it's going to be, but let's say like 20 something, 22 meters. This is maybe like 45 meters. And this is for 25, 75 meters. So you need to know this one. This is going to be the distance that you're going to draw on the horizontal line. So if this one is 0, 15, 30, 45, I'm doing every 60, right? So you start looking at the points. The first point is 15 meters, and you need to look at the elevation of the first point. Elevation is 10 meters. So let's say 10, 20, 30. The most important thing, don't forget to label axis elevation meters, and here you write distance meters. So this is going to be a 0.1. This is going to be a 0.2. Again, this is just a like rough example. 0.4, and you connect. This is just rough example, guys. I don't do it to scale. I mean, just give you some like basics how to draw it. So I want to go to next slide. Actually, explains a little bit more. It's about scale. So if it's 1 over 15,000, 1 centimeter, 15 meters. The elevation lines indicate the topography of the site. So that's what you're gonna draw as elevation points, 10, 20. So it all means meters, 10 meters, 20 meters, 30 meters, 40 meters. But we don't write meters, we just know that it's meters. We just write only the numbers. All the numbers are usually in meters. And BH indicates the location of borehole 1. Yeah, this is first borehole, second borehole. So you're also given borehole logs for each of the borehole. And well, the procedure that I just already tried to explain to you guys with my like rough sketches. So we start with, let's say, call it as a 0, and then the first point, second point, third point. So I think what I would suggest, if you have a borehole which is not sitting on any of the elevation line, you can, well, you're going to look at the borehole log and see what the elevation for that borehole is. So there is always information provided at what ground surface level this borehole was drilled from. And let's say it says maybe 1.3 meters. Sorry, not 1.3. It should be about like maybe 13 meters. So you also include this one for your ground surface measurements and drawing. So you get all this. Again, another thing that I would recommend, some students, what they do, they measure from here till here, and then this is 1 centimeter. Then they measure from here to here, and then this is like maybe another 1 centimeter. Then from here to here, like maybe 2 centimeters. You can still do that, but it's not a very good way. So the best way is you start from 0, and then you just measure from 0 till here, till here. So this is 1 centimeter, then this is going to be 2 centimeters. This is going to be like, I don't know, 3 centimeters. So do like that. Don't do like from like one point to another, because that's how students make mistakes. I've seen them doing this, and I always tell them to just like do it like at one go. Print out the map, find a nice ruler, put the ruler against this cross-section line, a dash, start from the first point, maybe make it as a 0, and then just measure the distance to the next elevation line where this cross-section a dash line crosses the elevation lines. And just like do it at once, just like do it like, don't do it like one by one. So this is going to be like the easiest and the fastest way to do that. Then you see like use distance. Don't forget to write units, elevation, also units. Many students, they don't write units, or they don't actually label their axis, and that's how they lose marks. So this is a mistake. Then you see like this is going to be, this is 10 meters, so it's going to be 10 meters this point. Next one is 20 meters, 30, 40. So you draw these points, and you connect them, surface. And so next step is you need to, like, your map always comes with boreholes. It has borehole 1 and borehole 2. You also, like, in borehole logs, you know the elevation. Like in this case, I'm not sure what the elevation was. Maybe it was 15. So you're going to find the location of the borehole on this cross section. So that's for borehole 1. This is for borehole 2. And you're going to use, this is very important, you're going to use this scale to draw cross section to the scale. As I showed you before, cross section, it has scale on the left, sorry, not cross section, borehole log. It has scale on the left hand side. It shows you depths, or it even shows the elevation. It depends on the borehole. Sometimes it shows both elevation from the ground surface, or just the depth of like soil layers. So you're going to use this scale that comes with borehole log, and use that scale as well. So and draw this borehole according to the scale on the left hand side. So if this borehole is, let's altogether 10 meters, so then from here till here it should be also 10 meters according to this scale. So maybe it was 20 meters here. So it starts from here till here, it should be 20 meters. And all the layers that you have in the borehole log, they also should be at the same level here. you use this elevation scale to locate the layers for each borehole, BH1 and BH2. Do you understand this one? You'll be kind of quiet, so I'm not sure. Okay, no. Why no? So the borehole, a bit confusing. Okay. So how about you have? I'm going to say this is borehole log, right? And this is says from 0 to 10 meters. And then this is going to be 2 meters it's sand, and here 8 meters clay, and here silt. So this is borehole. I mean, I just simplify borehole 1. Of course, like you have like more information in borehole log. And now what you're gonna do, like you drew your cross section, and you have a scale here. So and your borehole will be here, this BH1, and here you have elevation, let's say 20 meters, and then next one goes to 10 meters and 0, like this. And here you have distances, I don't know, let's say 10, 50. Well, typically it should be 50, then 100, and on this. So what you're gonna do is, you know where your borehole 1 is, right? On the ground surface, because you get it from the map. So, and you know that it's 10 meters deep. So what you're gonna do next is, you just look at this one. It's 20, and so it means that your borehole should go till here. So this is going to be 10 meters. So I use the scale on the left-hand side, the one that we use for elevation, to also draw this borehole line on the cross-section. What I'm going to do next is, I know that in the borehole, 2 meters of sand. So from, if it starts from here, 2 meters will be about here, which is 18, right? So it will be here. And this is sand. And then I know that next another 6 meters will be clay, and the rest is sealed. So that's what I meant when I said that you use scale on the left-hand side to draw cross-section, to draw a borehole in your cross-section. Is it a little bit clear now or not? Okay, so just your borehole can be deeper, can be 20 meters, can be even like 30 meters. So when you take this borehole log and apply it to the cross section, you just make sure that you use you adjust it to the scale that you already have on your cross section here on the left hand side. That's it. So if it's another 10 meters, then you can draw in another 10 meters here. So this is the kind of thing. Okay, so a few more things that I wanted to mention. There are different ways to draw a cross section. So the one that's shown here, you see how it has sort of like a little bit thick thick borehole, and it has some like this kind of rectangular box, and it has different colors here, kind of like brownish, then yellow color, and I don't know, like something like really dark. So this is one way to do that. Another way to do it, if you have a borehole, instead of color, you can use symbols. For example, we use dots for sand, we use lines for clay, or some other symbols for rock. You can also do that one. You can use the color, or you can use symbols. But what you need to do if you use this kind of things, you need to provide legend. Because if you give this cross-section to somebody with different colors or different symbols in it, they don't know what it means. So that's why it's important to provide legend. If you don't provide legend and you have the symbols or colors, that is going to be a mistake. So for example, in this case, when we have different colors, it explained that this dark color means it's sealed. I think it's here, sealed. Then this yellow color, it's clay, and this is going to be sand. So that's what we know. If you have symbols that you're going to have a different legend, you're going to draw a box. You're going to put dots and write sand. Another box and draw lines and call it clay. Another one, I use this kind of symbols. I don't know, let's call it sealed. So this is going to be legend for from this particular borehole block. So it's up to you how to do that. So another way that students can do, either way is fine. Just if you use symbols, you need to provide legend. Another way to do it, you can just draw a simple line for your borehole, and then you just mark each layer, and then you just write here sealed. Here you write clay, and here you write sand. Here you write sealed, clay, and sand. Of course, you need to write this is BH1 and this is BH2. So you can also do this way. It's kind of simple, but it's still correct. You can choose what you really want to do. Yeah, I mean, maybe it's not very like visually appealing. And also another thing with this style, right? If you don't have, if you have boreholes kind of far apart, that's okay. If you have like many boreholes, and then imagine then you have another borehole in the middle here, and then you do the same thing, you're gonna put like lots of information on the cross section, like text, like seal, clay, clay. Maybe not like a good way to present it. But again, it's up to you. If you have 3 boreholes and they're kind of like apart from each other, far like away from each other, so you can do that way. So it's up to you. In this case, because you already explained, there are no symbols to explain, you don't really need to provide any legend. You only provide legend when there is something that you need to explain. Something that like color or like symbols. Another thing you see, like this is little triangles. That shows you water level, groundwater level. So in each borehole, if there is groundwater level, you can know the depth, groundwater level. You put a symbol, which means groundwater level. That should be enough. So it means at this level, there is water all the way down. There is water, here water. But you don't need to draw this one, what I did right now. Just like put a symbol and symbol. Okay, another common mistake, I'm not talking about common mistakes. Some students, what they do, they connect layers. So they think silt is here, and another silt here. Let's just, it's one layer. Connect. Clay, 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 connect. That little simple means groundwater level. So this is groundwater level. Means water. So the symbol should be drawn like this. And this will be at the level of groundwater. So like if you have a scale here, right, elevation, so it should be correct level. So this line shows where the level is, not like this symbol. So this line shows the groundwater level. Okay, so and then they connect this one too. And then they submit this to me, and I'm just deduct marks for this. The reason why you shouldn't connect layers with a solid line is that we only know what is in this borehole, and this borehole, but we have no idea what's in between. We don't know if this boundary goes like this way, or maybe it can go this way, or maybe like this way. We don't know, right? So that's why the best thing to do is, I'll just redraw it quickly. So the best way to do is you just use dotted line. So in this case, you say that, well, I think that there is the boundary between sand here and sand here, and it sort of going like this. So you don't make like a statement that, yeah, for sure the boundary between sand and clay it's here. You just assume it's here. Or just another way, just like don't connect layers, just without any lines or dotted lines. At some point, what we do at some point, we create models, and we'll have to connect layers. Yes, we do have to connect layers. When we like use computer software, we need to show like where the layer is, where the boundary between different formations is. So we need to show that one. But for this cross section, if you show it, just use this dotted line. Don't use a straight line, because this is kind of gives you assumption. I mean, like this is like what you assume. What if like you drill borehole and the boundary is somewhere here, and you like in your cross section you drew straight line? So in this case, you're going to be in trouble. You're going to be in a big trouble because you said, well, I know boundaries like at this point, but you have no evidence for this. Okay, so just be aware of this one. And another common mistake, students also connect end of layers. So if this one is still okay, this one is wrong. Why do you think this one is wrong? Like this line. It's still dotted line, so we kind of make assumption. But why do you think it's wrong? This is something that you're going to lose points for. Any idea? Okay, I will take it as no idea. So why you shouldn't do that? This is end of borehole, which means that they drill. Yeah, that's correct. So no info about materials below. So we just only know that we stop borehole at this level. We drill 10 meters. Maybe we said, okay, that's enough. Maybe we ran out of money, or I don't know. I mean, usually like you like drill like certain like length borehole, and you stop it there. And at the end, it was, let's say, sealed here, right? And here was sealed. But this is end of borehole. It doesn't mean that it's end of the sealed layer. If we drill it a little bit deeper, maybe till this level, yeah, that will be still sealed, and here will be like a bedrock. So the boundary is actually here. What we have here is the end of borehole. When you connect this end of boreholes, you make a statement that you think that the boundary, like the end of sealed layer is here, but this is incorrect. We just like don't have enough information. So don't like never connect end of boreholes. That's why. Do you have questions? Okay. What is the question then? So what you can do, guys, usually like in the class, in the laboratory, like students practice, they draw like by themselves and then show it to me and I give them some feedback. What you can do is, remember that file that I showed you, like from previous years, the one that I said I give to students when we have face-to-face class? So I'll just change it and show it to you. So what you can do, you can practice a little bit at home to draw a cross-section from that map and using boreholes given to you, and then show it to me during next class. Or you can just maybe like arrange some meeting with me. And then you can just practice a little bit. I'm not sure how you can define the partition of silt, clay, and sand inside the bar. Inside the bar, you mean like this bar? So you have the borehole log. Look, again, I'll just, yeah, it's from the borehole log. Yeah. So whatever you have, like, I'll just go back. I'm just showing my screen with you. I will share it, share application screen. So you see that for here, this is the borehole that you deal with. So you see that here, first 40 centimeters down, you have silty clay. And then you see that from 40 centimeters down to almost 7.6 meters, you have another thick layer, which is silty clay. So this is how, like, you know, the boundary. And then from 7.6 to 10 meters, you have clay. And then it says terminated, so which means that they stop drilling the borehole. Maybe if you drill more, there's going to be like more clay. So this is where you get boundaries from. And then you see what you can do, like for this map, for this borehole, it gives you elevation. So you can just like use these elevation numbers and just apply them to your cross section. Your cross section is going to have elevation, and you just look at the scale on your cross section and use this elevation to mark the boundaries between these three major layers. And you have groundwater level here. Okay, good. On computer, instead of printing out the map, to use the pen and paper. Yes, if you can draw on a computer, it's up to you. I think drawing on the paper will be a little bit easier, but if you're really good if you have some software and you're really good, yeah, that's fine. Yeah, just make sure that you don't connect layers with a solid line, because I've seen like many students using computer software. They draw a straight line, they put all the symbols there, and it's just not correct. Just as long as it's correct, it doesn't matter by hand or like by means of computer. I kind of like it when students draw it by hand. They always like very nice drawings and very colorful. So, but yeah, that's fine to do it by computer. Depth and elevation, they're different. So let's say if your elevation starts from 20 meters above the sea level, then but your like depth starts from 0. So elevation, it's something. I'm not showing anything right now. Presentation, I don't show anything. No, actually, there is no more content for today. It's already time to finish. I just wanted to show you guys how to draw that one. And if you want to practice, please practice. You can find that file on the course content site. Yeah, it's already like where we actually need to finish. So tomorrow there is a quiz, and well, thanks for joining, everybody. And thanks for asking questions, because like I just talk, and I'm not sure how much you understand. when you ask questions, I know that you are first of all like listen to my presentation, and also if there is something you don't understand, I would like to like explain to you so that you will do better in this course. Well, then everybody, thanks. I'm gonna get ready for my next session. I will have a tutorial today. I think it's from 12. Have a nice day, everybody, and I'll see you